Hi, everyone in the chat. Are you able to hear me? Perfect. Yeah, we're gonna wait a few minutes and then get started. So how I'm going to run this today is I have an old practice exam. I'd like everyone to please mute your microphones and chat as well, just to avoid interruption. I have an old practice exam. We're gonna do most of it, except oops, I didn't mean to have this filled already. Let me go ahead and erase this.
A lot of people.
Yeah. Hey there. All right, so we're gonna do most of this exam. We're gonna skip questions 4 and question 4, just 4 and 5, just in the name of saving time. And then we'll continue at this question. All right. And how you're gonna notice something when we use this when you're doing a computer architecture exam, you're gonna get an annex at the end. And you're going to be referring to this for pretty much every question, right? Because you're not expected to memorize the execution table here, all the micro instructions. You just need to know what you're looking for in the tables and how to use it. All right, so we will wait 4 minutes and get started at 2:05. Hi, everyone. Welcome to the Computer Architecture 1 Cookies and Cram. My name is Ethan. I'm the VP Social of IEEE uOttawa. In case you didn't know, IEEE is the Institute of Electrical and Electronic Engineers, and we are the sub-association for electrical, computer, and software engineers here at uOttawa. So let's get started with our Compark 1 practice exam. All right. So this is a question that was on one of my own quizzes, which a lot of people actually struggled with. In the name of time, we're just going to get right to the exam, though. There's a similar question later. All right, so this is a pretty simple one, multiple choice here. So for 1,000 memory locations, now a memory location, and we need 1,000 of them. That means we need 1,000 different memory addresses. Because we're in a binary system, we need to have at least 1,000 different combinations that we can represent with a binary number. So this is pretty easy. We can literally just take a calculator and punch in 2 to the however many address line. 2 to the 8 gives us 256, and that's not enough. 2 to the 10 gives us 1,024, and that is just over 1,000, which means for 1,000 memory lines. Are you done to like calculators? Okay, well, its power is a 2. You'll just they're pretty easy. You know, you'll just have to do them in your head. Either way, 2 to the 10 is 1,024. So that's going to be our answer here. All right, next question. Which CPU register provides the address from which the next instruction opcode is to be fetched? All right, so what we can, excuse me guys, quiet please, thank you. All right, what we can do is we can go to the end of our exam and look at our annex here, and we'll actually see, we're looking at the 16-bit basic computer. We can go here and we see the actually it's not even printed in here, that's weird. All right, well, I have a second version which we'll use here. You can see here the PC, the program counter, gets loaded into the address register, and then it gets incremented. So the program counter is where the address of the next instruction that will be executed is. So the answer for this one, program counter. All right. Hi there. No worries. Yeah. Right. So this question, this is more, this isn't really Compark. This is more of a, what's it called? Digital systems question. So we have a mux and a full ladder, and we're saying an arithmetic unit performs basic operations on 2 numbers A and B under the control of 2 bits, S, we call that select, and C and carry in. And we can see what happens here. So when S is 0 and carry in is 0, we do A and B, which is addition. When S is 0 and Cn is 1, we do A plus 1, we increment A. When S is 1 and Cn is 0, we're going to do A minus 1, so that's a decrement A. And then when S is 1 and Cn is 1, we're going to do A plus B complement minus 1, which is the same as A minus B, right? So what we have here is we have to determine what the inputs to this multiplexer should be. So we should break this down into individual parts here. So we'll start with S0, C0. That's going to be the input for D0, all right? So, and this is for bit I, so it's not a specified bit, it's just any bit. But if you were to add A and B, we'll say A is a 4-bit number, so we have A3, A2, A1, A0, B3, B2, B1, B0. When you add the bits together, you add A1 plus B1, A2 plus B2, basically bit I of A plus bit I of B. And as we see here, we already going into the full ladder is AI. The second input into the full ladder will come from the mux, and since we're at 0, 0, D0, we just want to add the I bit of B. So what's going to happen is D0 will just get BI. All right. Next question, next part here. We have a S0 and Cn is 1. We have F is equal to A plus 1. So when we do that, actually I can get that back. When you have any number and you want to add 1 to it, you just add a 1 in the least significant bit, and then it's just 0, 0, 0, right? So since we have actually, sorry, I got that wrong. Remember, S is 0 and Cn is a 1 here. So what's going to happen is we have a Cn, which is attached to the select, and it's also going into the full ladder as a carry in. So when this carry in is 1, it's gonna still add 1 to A to A here. So if we want to increment it, all we have to do is enable the carry in bit here, which will add 1 in the full ladder to A, which means we don't need to do anything else to increment A. And we're actually just gonna give this input here is 0. All right, 2. So that's gonna be this one here. That's S is 1 and Cn is 0. We have F is equal to A minus 1, and that is going to be to decrement A. So if you want to do A minus 1, you do A plus 1. Oh, yeah, go ahead.
Okay, so when we increment A, we use the fact that Cn is equal to 1 increment.
Exactly, because Cn is also attached right to the carry in of the full ladder.
So what would happen if for some reason you give a table where F is equal to A plus 1, 0, and Cn equals
I'm going to tell you that that's not going to happen.
Okay.
Just because this is even up here in this first question. You see here, you have this plus 1, and then you have minus 1, which is really 1 complement plus 1. Same here, complement plus 1. You get all these plus 1s, and whenever you have a plus 1, it's always tied to a certain bit. So here it's actually when x is 0, so you're going to take a x complement and put that into carry in, I believe. I'll have to confirm that. Yeah, actually here it's actually already complemented, so you just put an x there, and that's going to be your carry in. Okay. Maybe if we have time at the end, I'll go over this question because that was on a quiz or midterm of mine a while ago. Anyways, we're going to decrement A. So remember, when you want to subtract number, you take it. So in this case, it's 1. So 1 in binary, that's going to be 0, 0. We'll say it's 4 bits, 0, 0, 1. When you want to subtract that, you complement it and then add 1, right? So look how, no matter how many bits this number is, when you're subtracting 1, the binary equivalent of -1 is just every bit's 1. So we want to add -1, which is just 1, 1, 1, 1. So every bit's a 1. We're going to go ahead and just put a 1 in. All right. And now, last one is here. We want to do subtraction, which is F is equal to, or the output is equal to A plus B complement plus 1, which is the same as A minus B. So remember, Cn is 1. So we're already getting our 1 from there. So all we need to do is put B complement in. So it'll be just B. And it'll be the complement of all those. And then after we get our 1 from the carry in, and that will be our subtract, that will complete the subtraction. So all we're taking is the complement of bit I of B. So we're going to get there. BI complement. It looks here, actually, they use a different notation just because it's easier to type on a keyboard. BI and then a little apostrophe. So I'll go ahead and just do that. BI apostrophe BI complement. So that leaves us with, we have a bit I of B, a 0, a 1, and then bit I complement. We look here, that lines up here with, oops, selection D. Go ahead and highlight it. There we go. So that's our answer for that. Any questions here? Go ahead.
Whenever an arithmetic operation is -1, we just input 1 for every.
So for this question, yes, because if we look at the inputs we're given, when we're doing -1, we're not giving anything to the carrier. And we just have to decrement A, which is just -1, right? So that's A plus -1. And what's the and when you take the 2's complement of 1 to get -1, what do you get? Remember the 2's complement of 1. We can erase all this. Well, if we have 1, how do you take the 2's complement?
1, 1, 1, 0
Yep, and then
plus 1. Yeah, I don't know, but like, does this work for all situations? Like every time, like -1 would be.
well, the trick is you have to give it, when you want to subtract something, the second operand that gets fed into the full adder is 1, 1, 1, 1. So you have to implement whatever logic it takes to feed that into the full adder. And here, since it's just a mux, we just put a 1 on the appropriate selection. All right. Is there another question in the back? Awesome, thank you. All right, we'll go to the next question. All right, so the block, this is I'm assuming they're still doing the basic computer. You guys have talked about that in class, the 16-bit. Excellent. So quick review of we got someone in chat there. All right. We've got how the instruction setup works. So there's 3 types of instructions in the basic computer. There's the memory reference instruction, the register reference instruction, and the IO instruction. So, and that's determined with these bits here, bits 12 through 15. Those 4 bits are what determines what type of instruction it is. So if bits 12 through 14 are all 1s, then it's either going to be a RRI, register reference, or an IO instruction. And it determines between that using bit 15. But if these 3 bits here are not all 1s, then that means it's a memory reference instruction. And the instruction we select is going to be all the way at the bottom. And it will be one of these, right? We have 0, 1, 2, 3, 4, 5, 6, right? Because we have 3 bits. If the only combination we can't use is 1, 1, 1, which is 7, means we get 0 through 6 left. And then we have our indirect bit, which is used to do indirect operations. All right. So what's going to happen now? And I've just copy pasted this just to have it on the screen next to me, just to have it handy, because you're going to be referencing these charts a lot. I actually have a few printed out next to me just for my own reference, as well as some other stuff. So at some point, the content of the program counter of the basic computer is 3AF. All numbers are in hex. And the content of the accumulator is 2EC3 as shown on the following table. The content of the memory is partially given below as well. What is the instruction that will be fetched and executed? So what we're going to do is we are just going to go through this chart. I think I actually have it open another way here. Yeah, I have it open here. This is just another version of that chart. It's the same thing. We're going to go through the chart one by one. So we always start at fetch, then we decode. If we're doing a memory reference instruction and the bit 15 is high, or the I bit is 1, then we're going to do our dereferencing, which I'll show later. Then we go into our execution of the instruction. If we have an AND instruction, we follow these and so on. So let's go back to here. So program counter currently has 3AF. Here's what's in memory. So what is the instruction that will be fetched and executed? To do this question, I find it easier to actually fill out the last column first, just the last part there, just because it kind of walks us through the whole question all at once, right? So first, what happens is the program counter is copied into the address register. So 3AF will go in there. Next, we excuse me. Next, we copy we go to the memory address of the value in the address register. So the address register has 3AF, and we copy that into the instruction register. So what we're saying is that the instruction we're going to execute is at memory location 3AF. So 3AF, there it is, 93AD, and that's going to get copied in the instruction register. AD, excellent, handy. All right, and then next is the decode. So what we can do is we are going to figure out what operation that is. And remember, the operation is determined by the last 4 bits. So that's the high bits in hexadecimal, so that's 9. If we were to go look at that table again, we're going to find that 9 is an indirect add. Yeah, you're right, actually, yeah. Yep, you're right, I missed that. Sorry about that. Good catch. PC is going to get incremented to 3AF plus 1, 3B0. Sorry about that. Good catch. So 9 is an indirect add. We'll just keep that in for later. Well, actually here, since we're here, what is the instruction that will be fetched and executed? Well, that's going to be an add instruction. And then what we're going to add is 3AD, but indirect. So I, which is for indirect, and we'll go over what that means in a second here. So indirect, because our I bit is high, and we're not doing a register reference instruction or an IO instruction. That's what it means when it says D7 is low. We're going to go to the memory address that is currently in the address register, and then overwrite the address register with that value. So 3AF, where did I go? Memory address 3AF. Actually, did I miss? I think I missed writing something down here. I'm just going to restart. I got a bit confused earlier. So let's start over one more time. PC gets copied into AR. 3AF. Next, we copy the memory address that's currently in the address register into the instruction register. So you go to 3AF and we see 93AD, and we copy that into the instruction register. And then we increment our program counter. Perfect. Next, that's right. We copy so we have our instruction register, and we copy the lowest 12 bits into the address register, because that's the address we're going to be working with. So IR 0 through 11, that's these 3 bits, or 3 digits, 3AD. Copy that into the address register. And now what's going to happen is, since it's indirect, we're going to dereference it. So M of AR, we're going to go to address register 3AD and throw that into the address register again. So that's address 3AD has 303B5. All right, there we go. Let me put that up a bit. They don't give us much space. Perfect. And now, I'll just go back to this chart here because it's handy. We're doing an add. So we've already dereferenced it. We're going to do our add now. So what happens is we copy the contents of memory at address AR into the data register. So AR currently has 3B5. We go to address 3B5, 3B9F. We put 3B9F into the data register. Just like that. And now, go to our next one. We do data register plus the values in the accumulator gets put into the accumulator. Our carry, if we have any carry out, it's going to go into E, and we reset our sequence counter. So what's going to happen if we look here, the accumulator has 2 EC3 plus what's in the data register, 9F. I've already gone ahead and done this. It comes out to 6A62 with no carry. So the accumulator will now have 2, and also forgot to mention here, when we did our decode and we determined that it was an indirect instruction, we put a 1 in the I, and we have no carry, so E is going to be 0. And remember, we said we reset the sequence counter. We're going to have some nice zeros in there. And that's what the table is going to look like there. So let's make sure I got that all right. Yep, great. So we've determined that we're adding the values in at address 380 indirectly, and we're going to put that in the accumulator. Now, what we're going to do is show the operands in the binary operation that will be performed in the accumulator when the instruction is executed. We just did that over here. It's 2EC3 plus 3B9F. And so let's put that here. Perfect. And we've already filled out that column there. All right, so that's it for the question. Any questions here? All right, great. Next question. What is the result of this program performed by the following assembly program? I just went ahead and added these lines in earlier just to make it easier to write later. So first off, we have symbols here. So LDAOP, we've given this address. These are all addresses in memory, each of these lines. We've given this address in memory the label OP. So we have an LDA and it's not indirect. What we're just going to do is load the value at OP into the accumulator. So LDA is just load. So I'm just going to put over here.
What's origin 100?
Oh yes, that's origin. So that means that it's when you're writing your own programs for the base computer, it's a way to say, because you can't just write, when you're writing text, you can't say this is address 100. This is to tell, it's more of an abstract for this course, but it's saying the next instruction here is will be 100.
Oh, okay.
Yeah. So LDAOP, it means OP is going to be loaded into the accumulator. So accumulator will equal FFA5. CMA, that's a register reference instruction, which means to complement the value in the accumulator. I've gone ahead and have done that already just because that's not really the scope of this course. That's digital systems. You should know how to complement binary numbers by now. The complement of this is 005A. Increment, we're going to add 1 to that, equals 005B. And now we're going to add OP1. So we go to OP1, that's 0039 plus a value in the accumulator, 005B. That's going to come out to 0094. Yeah. 94. And now we're saying STA, which is to store at memory location OP2. OP2 just has a 0 in it, so I guess we're storing it at there anyways. So what's going to happen is when we say STA OP2, the memory of OP2, which is address 0, will equal 0094, just like that, right? Halt. Done. All right. OP1's right. Yeah, that's called the label. Okay. Now it says the machine of this program is stored in a memory unit of 1 kiloword of 16 bits implemented in Altera. You remember that. Give the Quartus memory file that describes this program. All right. So remember here, we have org 100. So our next instruction will be, why is this doing this? Okay. There we go. This is going to be 100, 101, 102, 103, 104, 105, 6, 107, 108, and that's end, so we don't need that. And they've actually helped us out here a bit. They've given us some so we're saying LDA OP is at 100. LDA direct is the hex code is 2, so that's 2, and OP is at address 107. So we're starting here 2107. That's our first one. Next, our next address, our next instruction in this program will be located in this block at address 101. So that's 100 plus 1, and that's going to be a complement. So complement, if we look at our table again, you'll find that the code for this instruction is 7200. All right, next we have increment. The code for increment is 7020. Then we have add OP1, so add is opcode 1, and then OP1 is at address 106. All right, next is STA at OP2. So store, that's opcode 3. And then OP2 is at where was I?
108.
108. Yep, that's right. All right, and then halt, that's just 7001. And now if we look here, now we're at address 106, and these are going to hold these values, right? So it's 106 will hold OP1, which is 0039. 7 will hold OP, which is F5. And sorry, earlier I got a bit confused when I said it's storing it at address. That's not true. It's storing it at address 108, which just started off holding the value 0. So when this program is initialized, address 108 will hold 0. And then I guess I should put 4 zeros for completeness. And as you can see, we don't really have anything else there. So that's actually the end of the program. Just fill all of these with zeros and you're good. I'll just, I'm looking at the solution here and it's got all zeros. All right. It only takes a second. Actually, I don't know if you're doing bright space exams, they're kind of picky with your inputs. Okay, that's good. It only takes a sec. All right, just put zeros. Yep.
So how would you know that's a 2?
So remember, LDA, that's an opcode. Yeah, if you look in the annex, here, it's not that one. It's not LDA. It's LDA is direct. LDA is direct. And then remember, OP is just a symbol for when you write text, assembly text. OP is just a symbol for 107. So we're saying LDA, which is code from 107. That makes sense?
And then you have
yeah. So just add is and then OP1 has address 106. Yeah. What? And if you'll get this like this on your exam. Sorry, I got something going earlier. But, you see here we have LDA, and it says 2 or A. It's 2 if it's direct, It's A if it's indirect. And notice how there's no I anywhere, like how I wrote up here, add 380I. The I means it's indirect, which means that the last bit 15 is high, so that's 0 to 1. Yeah, if you're writing it in text, yeah.
Right, so if it was, in fact, it's an LDAI.
Yeah, I'd say LDA OP1I.
Oh, in the I.
And then you would use the.
All
All right, any other questions for this? All right, we're gonna go to the next one. I'm going to go ahead and skip this question for now, just because the solution's a mess, to be honest, and I don't think anyone's gonna, I've never understood it myself. It's just so much of a mess.
What was the question about?
Okay, so it's, you have you have to expand the basic computer. I'll just show you what the solution looks like. It's incredibly unorganized. This is 5 multiple pages long. Yeah, so here's part of it, and then here's another chart. It's very long, and honestly, questions on the exam. So we're gonna. I don't think you will, because it's long, but either way. We're gonna go here to the next part.
Oh, you guys have the same exam?
That's awesome. It means you can't ding me for reusing it. Okay. So this is I'm guessing this applies to another exam because we're restarting at 1. Either way, let me just get my notes here. Consider the following logic diagram, and you're given some values. So here we're given some values here to start with. You have to determine what the outputs are here, and then you have to do some conversions and make sure the value is correct, right? So if you look at this, this is a full ladder with the subtraction toggle, right? If you have M as 1, it will complement your second operand and put 1 in the carry in to give us the subtraction. So we're going to do here. Here, all right. What is your calculations in the last 2 columns of the following table, right? So we're really just doing some nice binary addition here, right? So M is 0, which means we are not going to complement anything. Yeah, so let's start with the first one here. 1, 1, 0, 1. Give myself more room. Plus 0, 0. All right, so we just do our addition here quickly. What will happen is 1 plus 0, 1, 0 plus 1, 1, 1 plus 1 is 0, 1, 1 plus 1, 0, and then we're carrying out a 1. So our carry out of the last bit, C4, is a 1, and our remaining value 0, 0, 0, 1. So we're going to be what we're going to. Sorry, it's 0, 0, 1, 1, not 0, 0, 0, 1. That's the value that's going. What's going on with your camera there, dude? All right, I'm going to close this. Okay. All right, so that's what's got what our result is going to be when we put these 2 numbers together. We're going to carry out in the next part. We're going to verify if this instruction is correct or not, or if you have an overflow. All right. Next, what we have is the same inputs, but with M is 1. So what's going to happen is we're going to do basically a subtraction. So we have 1, 1, 0, 1 plus, remember, when we have M here, it's going to complement all the inputs coming in from B. So we're going to have 1, 0, 0, 1. And then at the very end, it's going to be plus 1. But we'll do that at the end after we're done here. So 1 plus 1, 1. So we have 1, 1, and then 0, 1. All right, so carry out. That's 1. And the result, where did that go? Should be, oh, right, I forgot to do one thing actually. Forgot to add that 1 I said we would add at the end from the carry in. There's our answer, carry out 1, 0, 1, 1, 1.
Where's the carry?
It's from M.
Also, M is the carry.
M is your toggle to do subtraction, and it goes into the carry in. Because remember, when you want to do subtraction, you complement and then plus 1. So this M does both that. It when you remember when you put a value through an XOR gate, and when the other input to the XOR is 0, you just get the value. When the other input to the XOR is 1, it complements it. So what this does, it complements all the inputs coming in from B, and then it adds 1 through the first carry in. That carry in ripples through. All right, so that's going to be the value that comes out. Now we're going to make sure that these values make sense, or did we get an overflow, right? So we're going to go ahead and do, just give me 1 second, sorry. All right, we are going to, we're going to convert these numbers to decimal and then verify our results. So, and since this is 4 bits and we're writing in 2's complement notation, you remember what it means when that end bit is high. It means it's going to be a negative number. So we look here. So if we have 1101 and we want to find out what that is in decimal. Take us to, remember, we do it with 2's complement again, but we remember since we have a 1, we're going to append a negative. So complement everything, 0, 0, 1, 0, plus 1, 0, 1, 1. I know that that is 3 in binary, and since that bit was a 1 and before, it's going to be -3. So 3. All right, and it's the same thing for the second one, so we'll do that here. And we had 0, 1, 1, 0, which I know is a 6 in decimal. 6, there we go. Then our just M was, we had a 0 for M in the first one, 1, 1, 1. Our result here was 1, 1, and that's positive. So that's going to be a 3, and it's positive. So 3. And then here we have 7, and that's positive because again, that's 0. Now we're going to verify if those results are correct or if an overflow happened. So -3 plus 6 does indeed equal +3. So that's correct. But -3 minus 6, because remember you're given a -3 and then we're given a 6, but it's M is high. So we're going to turn that into subtraction, is -9, which is not 7. So that means that's correct and an overflow has occurred here. All right. So are your results correct? Yes and no. First one's correct, second one's not. I just explained why. And expand your adder with a circuit that can signalize overflow. So this is something coming back from digital systems. 1, if you want to detect overflow in a full adder circuit, what you need to do is get your carry out, your most significant bits carries out and the one before it, feed that into an XOR, and that will be overflow, which I'll represent with B here. So if that bit was high, and if you were to go back through and figure it through this second operation here and keep track of those carry bits, you would find that that B bit would be high, meaning an overflow has occurred. So that's how we can expand our adder. Yep, go ahead.
We should not add the 1 as carry.
We did. Yeah, it was, I don't think I wrote it out. Oh yeah, here was it, and I just did it. This was the result without the adding the 1, and then I just put it on here. All right. Any other questions?
I still have the confusion. This high, we call it. And something about that.
So M, if you look at the data path of M, do it in a color. It's going down into this carry in this first full letter, and then it's going through to all of these aggregates. That's the comp. So remember, what do you do when you want to get the negative of a number in binary? Let's just take any number. 0, 1, 0, 1. All right. What would if you wanted to turn that into a negative, what would you do? All right, so, and choose complement negative, 1, 0, 1, 0. That's its complement, then what? Notice that that's exactly what happens when that M is set to 1. It adds a 1 through this carry-in, and it also complements all of the bits of the B input.
Okay.
Does that make sense?
Yeah.
All right, great. All right. Yeah.
But for the result of the question, 10111 complement, it would be -9.
Well, yeah, but that's not, well,
Okay, so you're just asking for the,
he's asking our input. These were our inputs.
okay,
You can't get if you were to subtract 6 from 3, you would get -9. But the number that was spit out by our circuit was a +7. All right, does that make sense?
to get the actual like the -9, you have to do something else.
We can't. Our logic overflowed.
Okay,
So our full adder doesn't have enough range to represent this.
so probably you can another associated.
We would need to actually have another bit.
Oh, okay.
Because remember, when we are using 2's complement of any, so here it's 4 bits. So we have a bit that represents the sign, and then we have 3 bits for data for the magnitude of the number, right? The largest number you can represent with 3 bits is 7. So you can't fit a 9 in there. Except because there's only a 0. Well, you have 0 through 7, and then when you get to the negatives, you can actually reach -8. But -9's out of range, so that's why it's not actually possible to get a -9 from the circuit.
All right.
Where will this recording be posted? We'll figure that out, and I'll post a link to it in the site on YouTube. Okay, we'll post a link in the site server afterwards. All right. Next question. Right. All right. Let me just get my notes. I got this one. Yeah. Consider the computer of lab 4. So remember, this isn't the basic computer that was going like the textbook used. This is the computer that you would have worked with in your labs. So that uses 8 bits and it works a bit differently. The architecture of which is described in figure 1 and tables 1 through 5. I'll show those quickly after. The instruction type is determined by the 2 most significant bits of the 8-bit register IR as follows. So if IR7 is low, chat. Thank you. If IR7 is low and IR6 is low, that's a memory reference instruction. And that's just to make it simple, we have some logic that raises this X0 bit high. IR7 is low, but IR6 is high. That's a register reference instruction. IR7 is high, IR6 is low. That's a memory reference instruction with indirect addressing. Assume that all registers are equipped with 3 control bits for loading the register. Increment by 1 and reset to 0. Find the list of all micro operations which change the value of the accumulator, and then derive the logic equations or draw the logic diagram of the control circuit of a. So we actually for this one, we're gonna have to go look at our tables. So that's the lab 4 computer. Here it is. So the questions were, find the list of all micro operations which change the value of the accumulator. So if we look here, we have it. I have it highlighted here. So just give me one moment here. I'm just going to review the answer just so I can give a clear explanation here. Either way, you will be referencing these a lot during the during your exam, and I think actually, I think I know what's going on. My PDF did not print properly. Let me just open this up again. Yeah, my PDF didn't print properly. So all that you're looking for in this table, and you'll get this table on the exam. Remember, it's at the end here. Here. So we have memory reference instructions here. We have to find the micro operations, but go back too far. Next, here we are. Let's find the list of all micro operations. So here's the micro here's the micro operations for the memory reference instructions. And remember, the micro operations are the steps that make up the larger instructions that we're going to actually use in memory. So all we're looking for is all the micro operations that give us a that have an arrow that points to AC. That means that the value in the accumulator is being changed. So I'll just go ahead and do that actually on the annex down here myself. Here. So none up here. Go here. Here it is. So we see here that's a micro operation that changes it. There's another one. AC does not change here. It's loaded from, but it doesn't change. Here's another one. AC is changing here. And here's another one. AC is changing there. And almost all of these, the accumulators changed. Right. And should be it. Let's check the solution one more time. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think I missed the table. Function 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8. All right, sorry, I missed one. Let me just find it inside the table here. It can be a bit hard to see sometimes.
Aren't they all on the last page?
Are they?
I think
Did I
so.
get messed up? Oh no, this is for the a different computer. That's for the basic computer that's in the text.
Oh, okay.
Sorry, just give me one moment here and I will find my bearings. Oh, they're here. They were just cut off. Sorry about that. It's F is equal to AC. Yeah, so I believe it's these ones. It just has it listed a bit differently. You have T3 of XR1. You know what? Let's just I think we're just going to take a quick 5-minute break. Everyone can get a cookie, and I'm just going to figure this question out, and we'll come back to it. Sorry about that. All right, we are going to get started again in just a minute here. The host asked you to unmute. I'm not sure who the host is. All right, everyone get a cookie? Because I figured it out, we're gonna restart. It was just very odd formatting in the solution here. Either way, if we, basically what we want to do is we want to look through all the micro operations and find which ones edit or modify the values in the accumulator. So if we look here, we see, and this is just for, remember, this is for the 8-bit lab computer, mini computer, not the 16-bit basic computer in the textbook. We see in all of these highlighted ones, we have, we see that these all have modified the accumulator in some way. So if we go back up to our question here, I don't know why it gives us no space. Either way, find the list of all micro operations, which would change the value of register AC. What we would do is we would go take all of these instructions. So we would say give the inputs, which is T7, Y0. And then we say that AC becomes equal to the accumulator plus the data register. And that's one instruction. Next one, T7, Y1, those are our inputs. We have accumulator is loaded in, the value of the data register is loaded into the accumulator. These are all the micro operations that modify the accumulator. Now, the second part of this question says to derive the logic equation to draw the logic diagram of the control circuit of AC. We're going to do the equations, and if we go to the lab 4, where is the, right, it doesn't show the inputs here. Either way, I'm not sure where they went, but we know that all of these, here, this is what it is. All registers are controlled with 3 control bits for loading, increment, and resetting to 0. So what we need to do is we need to figure out what the equations are for these inputs. So we'll start with LD, with the load. So we'll call that LD. So AC, LD. What we're going to do is we're going to go find all of the equations where AC is loaded into, right? So if we look here, we have, so that's when we're just putting an already existing value other than 0 into the accumulator. So I'll just write it down here. So LD of AC T7 Y0. So these are all the signals inside the computer that we're using to determine whether or not we need to enable the load bit of the accumulator. So when these bits are high, that's when we have a load also. Plus T7 Y1, all right, plus T7 Y5, that's down here. T7 Y6, and then we have here, we have T3 X1, and then IR is 1. Let's continue. 3 X1 IR1 plus T3 X1 IR2. And then there's one more plus T3 X1 IR of 3. And again, if we look here, we'll see these are all the values where AC is loaded into, and that these other ones here, these are the only ones we haven't touched. These are special because we have 0 and increment, and as we recalled earlier, we have separate inputs for 0 and increment. So clear of AC. we're gonna toggle that when this signal is active. T3 X1 IR 0. 0. And then we have increment T3 X1 IR of, right, because that's increment. All right, sorry, that was a bit messy. And but one other thing we can do here, and you will be expected to do this on your exam, is to simplify your equations. You can see here we can factor out a T7 from all of these terms up here. And then from the bottom, we can factor out the T3 and also the X1, I believe. Yep. Yep. That's how we could simplify that equation a bit more. All right. So next question. So two memory reference instructions in the basic computer are to be changed to the instructions specified in the following table. All right, so in the following table, so we have symbol ADM, it'll take opcode 001. What will happen is we have this symbol EA, and we're taking the memory at EA, adding it to the accumulator and storing it back in the memory of EA. And the description is add the accumulator to memory, and B and A, which will be branch if AC is negative. So, notes out one more time here. In the following table, write down the necessary micro operations in register transfer language to perform the execution phase of each instruction. Note the execution phase of such type of instruction starts at T4, see figures 2 and 3. Note that the value in accumulator should not be changed by the execution of any instruction unless the instruction specifies a change in its content. To this extent, you can use TR to store the content of AC temporarily. All right, so remember what we said, the execution phase starts at timing signal T4. So let's just look at tables 2 and 3 again, just so you understand what I'm saying. Here. So here's remember this is the cycle of the basic computer, the fetch, decode, execute cycle. Up here, we have our fetch, decode, and then execution. Here, this is our indirect. We check if it's indirect. Execution is going to start at T4, which is down here. So EA is just some kind of abstract register that we're just going to assume is here for us to use. I don't think it's actually part of the computer. Yeah, it's not. So we're just given an extra register to use for this problem. So that makes it pretty easy. All right, so we'll start with 80M here. And oh yes, so remember opcode is 001. And if we remember down here in the basic computer, it decodes the opcode from the instructions. Remember, those are those 3 bits. Is there a picture somewhere? Either way, those are those bits 11 through 14 that make up the opcode, and we have 0 through 7, right? And when it gets decoded, if it's 0, then it sets this bit D0 to high. If it's 1, it sets D1 to high, so on and so forth. Since the opcode is 1 for this, we're taking over the bit D1. So on our first timing signal, which will be D1 T4, at this timing signal, we have this requirement that the contents of AC cannot be changed. And since we're adding it, we have to store it temporarily, right? So what's going to happen is we're going to temporarily store this value in this register we're given TR. So we're going to copy AC in there. I'm going to have to write small. Next. what we're going to do is we want to do our add. So remember, to add to the data to the accumulator, it has to be put into the instruction register first. So what's going to happen is we're going to load that value from address EA into the data register. All right. D1, T6, AC, we will then add in AC plus data register. And then remember, we have to store it back, that value back at address EA. So that's going to be M of EA. Copy the accumulator in there. Next. And also remember to put a value. If you look back at the data flow chart of the basic computer, the accumulator is not directly attached to the bus. So, but it is directly attached to the data register. So what we're going to do is we're just going to copy that value we stored TR into the data register. And then our last step, what's going to happen is we'll finally load that saved value back into the accumulator from the data register and reset our sequence counter. And in the comments, you could just write down kind of what I just said verbally. All right, now B and A branch if negative. So if the accumulator is less than 0, then we put the value of EA, so it's going to be an address, into PC. All right, so all right. Now we have a 0, 1, 1, and that's a 3, so that means our opcode, the signal is going to be D3. And all of this can actually be done in one micro operation. So the execution starts at the timing signal 4. And we're allowed to be a bit more verbose here, but if remember, since we're working in 2's complement and we're branching if it's negative, a value in 2's complement is negative if that last bit is 1. And these are 16-bit numbers. So if bit 15, 0, remember bit 15 is the 16th bit because bit starts at 0. If bit 15 is a 1, then we are going to do our branch. So if A, B, 15 equals 1. I'm just going to make sure I copied that right, just because the notes are pretty rough. All right, if AC is 1, yeah. 1. Then what's going to happen? We copy the program, we copy EA into the program counter. And SC will be 0. That's the end of the instruction. We reset back to sequence counter 0 to go on to the next cycle. Now, one thing that is I do find a bit strange is if we look here, we have this see here actually. These instructions. Yep.
If we're doing like a if, shouldn't we put the AC 5 into the equation? So it's T3, T4, AC 5.
Sorry, okay, say that again.
Okay. So if that's it, so on the first line, the second, if AC 15, so I know what I mean, but shouldn't we do D3T for AC 55 in the condition on the left before the?
No, because AC of, I mean, that would be one way of doing that, but AC of 15 isn't really a signal that goes around, and that's not an actual signal inside the computer. We just have the timing signals and we have those D signals, which come from the decoder. So this is something that has to be implemented with other logic that doesn't exist, but we're saying if the AC of 15 is 1, then we want to branch from to address EA. Now, instruction specified. Should not be changed. Now, the actual solution does, this is something I'm not certain about. The actual solution says it should be copied from the address register, but nowhere does it. It says I'm assuming EA is a register here, and nowhere does it say that EA gets copied into the address register, which is why I've simply put EA is copied right into the program counter like it does up here, instead of copying into the address register. Because even up here, it doesn't say that in the solution, it doesn't say that we branch to the memory, or we go to the memory in the address register, we go to the memory of value EA. All right, next. Question 15, column 3 of the following table shows the, let me grab my notes again here. Column 3 of the following table shows the content of a memory segment of a basic computer that stores a machine language program and its operands. Convert from binary to hexadecimal both the address and the memory contents, columns 1 and 3, and write your results in columns 2 and 4 respectively. And then we're going to use table 6 to convert the machine language program to symbolic operation codes, assembly language. Write the assembly language instructions in the corresponding cell, column 5, use hexadecimal, and then we're going to fill out the last column 6 of the table with the content of the accumulator after the execution of each instruction. All right. So again, I'm not going to go over the specifics of how to convert from binary to hex. I'm going to assume that we all know how to do that at this point in the course. If you don't, there's a million tutorials on YouTube that will go over it very easily. Anyways, so I'll pull this out quickly. All right, and then next set here. Right. So again, now what we're going to do is do our, we're going to convert these into our symbolic operation codes. So we're going to take it from we're going to look at the values here. And remember, those are our instructions. So what you're going to do for each of these is you're going to go again, and you're going to go to that table we know and love. And this is the basic computer. So we're going to this table. So you look at the most significant bit, and that will be your instruction. And then if it's a memory reference instruction, then the next bits would be your address that you're working with. If it's not, then the entire bit is part of the opcode. The entire number is part of the opcode. So Let's go back. Here it is. So. So 7, the hex code 7, that is a that's going to be a register reference instruction. 7800, that's a CLA. And when we do a CLA, it's going to set the accumulator to 0. Next, we have 281D. 2 is load. And then since it's a 2 and not an A, it means we're doing a direct load. So we're going to load from address 81D. So I'll just put that in words. LDA from 81D. Address 81D has this number in it, 0121. So that's going to get put in the accumulator. All right, next we have 181E. So 1 is an add. So it's going to be add. And then it's going to be from address 81E. Now address 81E has 000F in it. So you're going to add those together. And then if you do that, you'll find you get 0, 1, 3, 0. All right. Next 881F. So 8 is going to be a see here, actually, did I copy that right? Yep, 8 is an and, so that's indirect and, that's right. So we're anding address 81F, but indirectly, so and 81F indirect, and that's how we specify it's indirect. So remember, how this is going to work is we're not going to take the value in 81F and that within the accumulator. We're going to go to address 820 and then and this value 01C4 with the stuff in the accumulator. And when we do that, you're going to find that you get 0, 0, 1, 0, 0 in the accumulator. Next is we have a 3, so it's a store. 81D, and that's direct. When you do a store, if you go back and look at your table, you'll see that the values in the accumulator don't change. It's just a store. So it's going to stay the same in the accumulator. Oops. But you'll find that the value at 81D will become 0100, but we're not actually going to change this here because this is supposed to be a conversion of this value here, not we're not supposed to update it as we go along. And then our next one here, 7001, that's a 7, so that's a register reference instruction, and that code is just halt, which doesn't change anything in the accumulator. It stays the same, and that's the end of the program. These aren't instructions, these are the values we used in memory. So that's what we've done here. We've converted from binary to hex. We use the table to determine the symbolic operation codes, and we filled out the values that we're going to find in the accumulator afterwards. All right, question 6. What we're going to do, is there a question?
I think I don't know for a second. I find the address.
For which?
Like, let's say add 81E.
So
I need it.
the entire instruction is contained in this number, right?
Okay.
So, and it's a 16-bit instruction.
Oh, I'm seeing it now. Okay.
Yeah, so remember, it's a 16-bit instruction in hexadecimal. Each hexit or whatever it's called, it's not a digit because it's hex. Digit implies it's 10. Each value here represents 4 bits.
Okay.
So remember, those most significant 4 bits are going to be the instruction. The rest is going to be your address, or if it's a memory reference instruction, that's going to be your address. Otherwise, it'll be part of the opcode, right? 1 is a add. That's a memory reference instruction.
And then 81E is that.
Yeah, precisely. But when we go here to HLT 7, that's if you look at your tables, you'll see that that's a register reference instruction. Doesn't reference any memory. So what it does, it's kind of like a cheat to get more codes out of it. Since this doesn't need any memory, we just put 7, and then the rest of the number where we would normally put, where we would normally put an address, we use that as opcodes to get a lot more possible instructions. Any other questions?
Input output is F.
Input output is, it's 7 plus the indirect bit. Does that make sense, right?
Okay.
Like if you look at your table, it will show it as F. But remember, we how are you kind of representing it when we have these? We have 0 through 6. We have 7 to represent this, and then we also have that indirect bit. So if it's kind of like 7 is 0, 1, 1, 1. F is 1, 1, 1, 1, which is like if that indirect bit is high. So yes, it is F.
Okay.
And then, but you would also kind of look at that as using that indirect bit to get more value, since again, we don't have any memory addresses to reference, so we don't need to use that indirect bit to keep track of the memory address we're trying to get to.
Okay, gotcha.
All right.
I'm sorry, I couldn't go down, like, when you, the AND operation, so we, for 16 bit, and we just eat bit and we AND eat them?
Yeah, it's a bitwise and.
And so we transfer into like binary, and we do AND, and we
Yeah.
transfer back to text. Alright, thank you.
Okay, yeah, so we're gonna do our last question here. We're gonna write a subroutine called MUL in assembly language that multiplies two positive numbers by a repeated addition method. For example, multiply 6 by 4. The subroutine evaluates the product by adding the multiplicand 6 4 times the multiplier, i.e. 6 plus 6 plus 6 plus 6. I'm gonna zoom in a bit more so it's a bit clearer. Write your program using the instructions of the basic computer. Your subroutine should be stored in the memory of your basic computer with address A00. Before invoking your subroutine MUL, the calling program places a multiplicand 6 and address 9FFF in the multiplier 4 in the accumulator. The result is passed by a subroutine to the calling program through the accumulator. All right, so get those notes out here. All right. I think I'm going to go ahead and just type this for clarity. I'll just open up Notepad here. That's not showing very well. Okay, I'll do text instead and just zoom. All right, so one moment here. Right. Where's MLP from? Address 9FF in the accumulator. Okay. Okay, so what we are going to do first is set our origin. And we're specifying that's in hex at 9FF. So that means the next address is going to be, or the next, so imagine each line is going to be an address, right? And this isn't an address, that's just saying that when we're writing text, the next line is going to be 9FF. And remember, 9FF is where we've said we're going to store the multiplicand, which is 6. So this value, and we'll call this MLP for multiplicand, will be where we'll be at address 9FF, and is where we're going to place the multiplicand for our subroutine. So that's just going to be in it. We'll just say it's 0 just for the operation, because it's not actually being called. When it's called, we have to know to place it there. Next instruction, this is where our subroutine begins. Remember, it says our subroutine begins with A00. So 9FF, that's here. the next one, A00, this is where our subroutine is gonna begin. We're gonna give this the symbol MUL, as we were told before. We'll give this the symbol. When you want to do a symbol, you got to put a comma like this. And we'll say MUL, that's just a symbol, so we're gonna start there. All right, so remember what's gonna happen first. The multiplier is in the accumulator. All right, so what we want to do first is we want to turn that 4 into a counter, right? So we want to say we're going to do this 4 times. And an easy way to do that, if we look at our instructions, because we have the instruction increment and skip if 0, what we can do, if we turn that 4 into a -4, then every time we do that increment and skip if 0, it's going to add 1, check if it's 0. If it is, if we've done it 4 times, then we're gonna branch because it'll be the end of the subroutine, right? So remember that multiplicand is already in the accumulator. So what we're going to do is we're going to complement it. And then we're going to increment it. That's just because remember, if you want to turn that into a -4, it's complement plus 1. That's what's going to happen. Increment. And then we actually have to store this counter somewhere because we will need the accumulator somewhere. Go ahead.
Okay, so you make it 0, 0, 0, right?
Yeah.
And then you can complement it, but you never loaded value into it.
You were already told here that it's already in the accumulator.
Oh, then you complement accumulate.
Yeah. I'm just saying that there's no instruction here just because this is just a symbol.
Okay.
We're saying it's saying what will happen is when you call MUL, it will then go to the start at the next instruction.
Okay, that's going to probably.
Yeah. All right. And we do need to store this somewhere. So we're going to STA and we're going to store this at a new symbol called CTR. And we'll just put this at the end of our program. And it'll be initialized to 0 and it will be set to whatever that value is in the accumulator after it's been complemented and incremented. All right. Now what we want to do is actually clear the accumulator after we've saved that value. That's CLI. And now we have to enter a loop because we want to do this 4 times. So I'm going to give this another symbol, loop or LOP. And this is where we're actually going to start doing our work. So remember, we're doing repeated addition of the value here, MLP, the multiplicand, which is stored here, as long as that counter is not 0. So we're going to add MLP to the accumulator. And then we are going to increment and what the hell? All right, we're going to increment and skip the counter if it's 0. If the counter is 0. Like, yeah.
If execute after incrementing or before incrementing?
After.
If we want to see if something is 0, and if it was skipping 0, we want to decrement it.
We've already, so what we remember, we turned that 4 into a -4. So now we're incrementing it to get to 0.
Incremented and then you plus 1, it will be 0. If it's
Well, increment is +1, right? So it'd be -4 plus 1, that's 3, not 0. Plus 2, or plus 1, that's 2, not 0. Plus 1 is 1, not 0. And then plus 1, yep, it's 0. We're done. All right. I'm just gonna drink some water here.
the only incremented one for ISD.
So again, we're not done yet. We have I've said that we're making a loop. Do you mind showing the AND operation again? I'm guessing that was from a while ago. I'll go back to that after. All right, sorry about that. All right, so we're going to increment and skip if 0 the counter. And now this is the instruction we're going to skip if it's 0. We're going to skip looping if it's 0. And we're just going to end. And now I'm going to explain what this means. This is a branch unconditionally. When you call a subroutine, so here we're saying if you were to go say branch to BSA to MUL, it will store the return address here. So when we're done with our subroutine, what's gonna happen is you call this bun mul of I. We're not gonna branch to address mul, we're gonna branch to the address stored in mul, and that will take us back to where the program was originally called from. All right. And then that's actually the end of the program. So I'm gonna run through this with you quickly. So remember, we're saying origin hex and hex is 9FF. So this is 9FF, this is A00, so on and so forth. So we go to A00, our return address is stored here. Now, so we're gonna, the accumulator currently has 4 in it. So that would be we'll say it's 4 for now. We'll just stick with decimal to keep it easy. What's gonna happen is we're gonna complement it and increment it, so it'll become -4, and then we're gonna store that in this memory address called CTR. Right, I'll say that's counter, and then we're gonna clear the accumulator. So the accumulator has 0. Now we go here, and this is where we enter our loop. We're gonna add the multiplicand, which is stored at 9FF. So here we'll say it's 6. Pretend this is a 6, not 0. We're just going to say it's 6 from before. Is 6, increment and skip if 0 counter. So now it's -3, it's not 0. So we're not going to skip. We're going to branch the loop. We're going to do it again. 6 plus that here, which is 6, 12. Increment and skip 0. 2, not 0. We go back. Add it again. 18. So 1, it's not 0. Go back, do it one more time. Oops. All right, 24. Increment is give it 0. It's 0. Woohoo! So now, remember, we skip this next. We skip this next instruction. We branch unconditionally mul of I, or we branch to mul indirectly, which means that return address was stored in mul. We're going to go back to that return address and continue the program from where the caller left off. Does that make sense? Any questions here?
I have trouble understanding.
Sorry, say that one more time.
The-
Yeah. So remember, bun is branched unconditionally. It's going to go ahead and go back. It's going to branch to address LOP, which is a symbol, and here that's this line. So when we reach this, it's going to go back here, unless we skip over it, and that's when we actually exit the subroutine.
Subroutine, the main program is that in the subroutine, in the beginning, there's a return address and then like
So
return address will be, and instead of a halt, we just return back that return address.
exactly, yeah.
So that's the only difference. Okay.
Well, we didn't write a main routine here. We wrote a subroutine that can be called from a main routine. And yeah, subroutine doesn't halt, it returns, right?
Subroutine is just a subroutine.
I mean, you can make a subroutine that halts, but here we were told it has to return. So
Oh, okay.
what's gonna happen is, remember, your return address is stored in the symbol where the subroutine starts. So MUL is gonna hold that address that we called from.
So it has to be beginning the return address.
Yes.
Oh, I thought we wanted to capture the, okay, that's amazing.
But
And so the MUL, that value is going to get, like, in this case, it's already given to us. We don't need to change the value inside. MUL.
right now, since I just wrote the program, it's going to be, I just set it to 000. If you were to actually call this subroutine, what you're going to do is you're going to use the this instruction, branch and save address. Yeah. BSA, which is here. And that loads the program counter into the memory address specified by the address register, right?
Yeah, okay, so if we were to use BSA, then that would store the address where we left.
Remember the return address, because it'll actually store the next instruction, because program counter was incremented all the way up here. So it'll store the next instruction, because otherwise, if you stored the same instruction you were at, you would enter an infinite loop of just doing it over and over. So it goes to the next instruction when you return.
Oh, okay.
That make sense?
Okay.
Okay. Other questions? All right, so that's it for this question then. We'll do one more. Here it has a part 2. This part is independent of part A. The coordinates of a two-dimensional vector, ax, ay, r, and bx, by, are stored at consecutive addresses starting at f01. Write an assembly language program that calculates the scalar, the dot product, calculates the dot product, assuming that all their coordinates are positive numbers. The program is stored in memory beginning with location at address 100, and it has to place the product P at address F00. To calculate partial products, so this is where we're going to do that branch and save you should call your subroutine MUL, and then parameters have to be passed as follows. Remember, we put memory location, we put one value in memory location 9FF, and the other goes into the accumulator. And then the product is passed back to your program by subroutine MUL through the accumulator. All right, so I'm going to go ahead and again type that. So once again, our earliest address here is 100. So we're going to say, hex 100, and this is where our program starts. And this isn't a subroutine. This is a main program. So we don't have to do any symbols to specify where it is, where the subroutine is in memory. And we're just saying it starts at 100. All right, so first we're going to clear the accumulator. And then we have initialize 0. Oh yeah, and we're given, I should do this first. We said that we're placing the product P at address F00. So we can use ORG multiple times. Here I'm going to say F00 is down here just at the end, keep it out of the way, but we need to store our product P, and then we also need to store our products. We need to store our AX and AY and BX and EY. AY. So set our origin of hex to 0, clear the accumulator, and we want to store 0 in P just to keep it, make sure it's 0 so we don't get garbage data into our program and we don't build off of that. So now we're going to prepare to call our subroutine. So we have remember we have product P is at F00, and then memory location 9FF is used to store those 9FF is used to pass one of your parameters to your subroutine. So what we're going to do, and we're saying that their coordinates are stored at consecutive addresses starting at F01. Oops, I forgot the P actually. P, so that's F00, F01, F02, and so on. So we're making sure P is 0, our product starts at 0. Then what we want to do is we want to get our first value for our first value of a vector, and that's LDA of AX. We're saying that AX, these are all symbols, so we're going to LDA AX, and then we're going to store this in the memory location 9FF to use our subroutine. And remember, we've given that the symbol MLP, so we're going to say store it at MLP. Now we're going to LDA BX, which is our sec, because remember it's AX times BX, and one value is loaded into this symbol here, this address MLP, the other is put in the accumulator. So now we have AX at address 9FF, and we have BX in the accumulator. Now what we're going to do is we're going to branch and save address to MUL. That's our subroutine. So remember, what this is going to do is going to save the next instruction in this address here. And then when we're done, we're going to branch back. And it's the next instruction, because if we just saved this instruction, what would happen is when we go back, it would just immediately enter it again. So next instruction, we want to actually add that result to P. Add P. So remember, because the result of that multiplication is stored in the accumulator, we want to add that to our product and then do the next one. So add it to P. So that will be that sum will be in the accumulator. Store that value of P. Now we do all this again. I'll just copy paste this, but with our next values. So we don't load AX, we load AY, and then we're going to store that in that predefined location again. We're going to get BY. Again, we branch to MUL, and then when it returns, we're going to add that value to P. And now we're going to have we're going to have the sum of the two products. We're going to store that at P, and that's the end of our program. So we're going to halt. And just drag that up. And that's the end of that program. So any questions here? All right. Is there anything someone wants me to go over at all? Any questions for I'm going to post, I'm going to post a link because this is I don't have time to go over it today, but there will be a question about IEEE floating point standard. Now, that's the same IEEE here. IEEE is actually an international organization that holds a lot of standards in computing. And if you work in engineering, you will have to come across them at one point. The floating point standard is a way of how we can represent very large and very small numbers with a finite amount of bits. And it's a bit weird how it works, but there's a lot. I'm going to post a video. I will go over that. Yes, I will post a video about how you can, what the question will look like. It will either ask you to convert a number to floating point notation or from floating point. All right, and I will post that link in the site Discord server under the IEEE channel. All right, and the AND question. So that was this one, correct? The AND 81FI. All right, so what do you want to know about that? The indirect access. Sure. So when you do indirect access, what we're not doing is we're not just going to take the value that's currently in the accumulator and AND it with the value at 81F, which is an 820. What's going to happen is we're going to take the value in the accumulator, go to address 81F, see what the value is, and then go to that address, 820, and AND it with that value, which is 01C4. That makes sense? Okay, great. And yeah, so one thing that you will definitely need, you all need to understand this, I think I have a picture here, is how BSA works. I find a lot of people get tripped up by this. And I like this picture in specific because not only does it go over BSA, it also goes over indirect access here with your unconditional branch back to, because this is how a subroutine works, right? But yeah. All right. And should I do this here? Yep. All right. Any other questions before we call it quits? All right. Thank you all for coming. I hope this was helpful. If you have any questions, just let us know on the Discord. That's the best way to get a hold of us. Take as many cookies as you want. I don't want to take any home. And thank you very much.
Take the box.
Don't take the tin. I'd like the tin back.
Okay.
Thank you.